Hi guys, your Friendtor is here, and in today's video I'll be discussing the similarity and right angle triangles. Okay, so this is the second video of the second chapter, Pythagoras theorem from Max 2. Okay, so actually in this video we will be discussing those theorems which we will require or which will be required in the proof of the Pythagoras theorem and its converse. Okay, so without wasting time, let's get started. Okay, so the first theorem is, first let me choose a pointer. In a right angle triangle, if the altitude is drawn to the hypotenuse, then the two triangles formed are similar to the original triangle and to each other. Okay, so if you see in the diagram, triangle ABC is a right angle triangle with angle B 90 degree. Okay, angle ABC is 90 degree. Okay, and we drew, or we should draw a perpendicular BD from the vertex B towards the opposite side, that is towards the hypotenuse AC. Okay, so construct BD perpendicular to AC. Okay, such that A, D, C are collinear points. Then what we need to prove is these two triangles that are formed, that is ABD and BDC, are similar to the original triangle, that is they are similar to the triangle ABC, and we also have to prove that these two triangles are similar to each other. Okay, so three things that we have to prove. First, we have to prove triangle ADB is similar to triangle ABC. Secondly, we have to prove triangle BDC is similar to triangle ABC, and third, we have to prove triangle ADB is similar to triangle BDC. Okay, so actually it's very simple. We have discussed the tests of similarities in first chapter. If you don't know about it, please do watch my videos, lecture videos on chapter similarity, and there you will find all the details regarding tests of similarity. Okay, if you are very thorough with the first chapter, this proof is really simple. Okay, so I will provide the link in the description box if at all you need to refer about this chapter similarity. Okay, so let's start with the proof. Now here the triangles, first thing we will prove this part, triangle ADB is similar to triangle ABC. So whichever similarity you want to prove, in the same order consider those triangles in triangle ADB and triangle ABC. Okay, in these two, now we need to find two angles which will be equal, okay, to apply the AA test. Okay, now here the most easiest way is to apply the AA test, because we have information about the angles of these triangles. So first thing, in these two triangles, that is triangle ADB and triangle ABC, one, we have common vertex. Okay, A is common to both the triangles, and hence that angle is a common angle. So first congruency we got, triangle DAB is congruent to triangle BAC. Okay, name of the angle changes, but the angle is same. Name of the angle changes according to the triangle, otherwise the angle is same. Okay, so that's why the value of, or both the angle will be of same measure, since it is common angle for both the triangles. Next, we know that both the triangles have a 90 degree angle, that is ADB is equal to angle ABC is equal to 90 degree. Okay, so they are also congruent, each 90 degree. Hence we got two angles which are congruent in both the triangles. Okay, that means by AA test both the triangles are similar. Now in the same line we can prove the other part also, that is BDC and triangle ABC. Here also C is the common angle and 90 degree angle is BDC and ABC. Okay, so 2 points, angle BCD is similar, is congruent to angle ACB since it is common angle. Okay, and angle BDC is congruent to angle ABC since they both are 90 degree angles. Okay, so they are congruent. Again we got two corresponding angles which are congruent, hence these two triangles are similar by AA test. Okay, now we prove the first two parts. Okay, now the third part will follow. Why? Now this triangle is similar to bigger triangle, this triangle is also similar to the original triangle, that means they are similar to each other. Okay, so by property or by transitivity we can say that from 1, 2 and 3 we can tell triangle ADB is similar to triangle BDC is similar to triangle ABC. Okay, Simple. So let's see once again we will revise the proof and before going forward. Now here what we need to first important thing is the statement. Understanding the statement is really important because that is what we are going to apply later. Okay, proof is very simple. What the statement says, when you have a right angle triangle, from the 90-degree vertex towards the hypotenuse, if you draw a perpendicular, that would be the altitude of the triangle. Okay, but from the vertex of 90-degree towards hypotenuse, if you draw a altitude, the two triangles that are formed, okay, will be similar to the original triangle ABC, and they are similar to each other also. That is what the statement says. Clear? And then the proof is really simple. We are just applying the techniques that we used in the chapter similarity. Okay, so let's see the next theorem. Okay, so the next theorem that we are supposed to learn was theorem of geometric mean, and in that we will require the definition of geometric mean. So geometric mean of x1, x2 till xn, that is n terms, okay, is given by gm is equal to nth root of x1 into x2 into till xn. Okay, so geometric mean is given by nth root of products of the n terms. Okay, so suppose you have two terms. B is geometric mean of A, comma C. Okay, A, comma C are two terms. Then by definition B is same as square root of B into C. Not B into C, A into C. Okay, square root of the product of the terms will be the geometric mean, right? So if B is the geometric mean of A, comma C, that means B is equal to square root of A into C. And this is same as, we can write it as, if we square both the sides, from here the square root will vanish and from the B will get squared. Okay, so B square is equal to AC. So this equation is required. This we need to recall the definition of geometric mean so that we can interpret the next theorem its statement. Okay, so when you have two terms and if B is geometric mean of them, then that means B is root of A into C and B square is equal to AC. Okay, theorem of geometric mean. In a right angle triangle, the perpendicular segment to the hypotenuse from the opposite vertex is the geometric mean of the segments into which the hypotenuse is divided. Okay, so again, just like the theorem we learned previous theorem that we learned, same construction we are doing over here. We have a right angle triangle PQR where Q is the 90-degree vertex, and from Q we draw a perpendicular or an altitude on the hypotenuse. Okay, then we get two triangles. Okay, just like the previous theorem, same construction we have done here. However, the statement of theorem of geometric mean says this line QS is geometric mean of PS and SR. Okay, this QS is dividing the hypotenuse into two segments, segment PS and segment SR. Okay, the statement of the theorem says QS is geometric mean of PS and SR. Okay, that means by definition we need to prove QS square is equal to PS into SR. Okay, so that is what we have to prove. So to prove QX square is equal to PS into SR. Now how to reach there? We will use the statement of the previous theorem. What we know, in right angle triangle PQR segment QS is perpendicular to hypotenuse PR. Hence triangle QSR is similar to triangle PSQ. So we learned that when we have a similar construction, the two triangles formed are similar. So that fact we are using here, triangle QSR is similar to triangle PSQ. Now by definition of similarity, we can write these ratios. QS upon PS is equal to SR upon SQ. Okay, similarly QS upon PS is equal to SR upon QS. Now SQ I can write it as QS. Okay, now we will multiply the denominators to the other side. So QS into QS will become QS square and PS into SR will get multiplied by PS over in the right side. Okay, so QS square is equal to PS into SR. Very simple proof, right? But the tricky part over here is you should remember the definition of geometric mean. Okay, what do they mean by geometric mean? Then only we know that what we have to prove. So QS is geometric mean of PS and SR means QS is square root of product of PS and SR. That means QS square is same as PS into SR. Okay, that is the definition of geometric mean, and that is what we have to prove. Once you know that what we need to prove, then the rest part is really simple. Now with the same construction you will use the statement of the theorem, previous theorem that you learned, that these two triangles are similar, and then write the corresponding sides ratio. Now here QS matches, so QS square is equal to PS into SR. Just two-step proof. Okay, but remembering or being able to recall the definition of geometric mean, or just understanding the definition of geometric mean is important. Okay, otherwise the proof is really simple. So I'm done with the video. I just wanted to discuss the theorems that we will use, or the concepts that we will use in proof of Pythagoras theorem. And the proof of Pythagoras theorem and its converse we will discuss in the next lecture or in the next video. Okay, thank you for listening to me, guys. If you like the video, please share it with your friends, and please subscribe the channel. And you can also follow us on Instagram and post your or DM your queries, and you can also write any doubts regarding the videos or lectures in the comment section, and we will respond as soon as possible. Okay, take care.